Hello everyone, my name is Vincent Reniers from KU Leuven in Belgium, and today I will be presenting my schema recommender for NoSQL document database systems. So in the last several years, the database landscape has changed quite drastically, and is no longer solely dominated by traditional relational database systems such as MySQL, but we also see other categories of database systems such as NoSQL or NoSQL. And it's this latter category which I'll be focusing on. If we look at the data models of NoSQL databases, they are quite diverse as well, and they vary from graph to key value to columnar stores, which are more table-like. But today we'll be focusing on the more flexible data model, namely that is present in document-based systems, which is a more JSON-like format, common in systems such as MongoDB. So what exactly is the challenge with modeling documents or document database schema design? It's that they're more aggregate oriented, so they tend to lean more towards a denormalized format rather than a normalized form such as common in relational database systems. So if we look at the example, we see a customer that has placed an order for several products. Formulated as order lines, and the information on this order is all grouped together in a single object. So it's not split across several tables as is common in the normalized form, but it's kept together. And the reason for this is that it's typically stored on a single node. So now when this information is retrieved, it can be done via a single lookup on a single physical node, rather than joining all this information together from physical nodes from the different tables. So this benefits greatly read performance, but it comes at a downside in data redundancy. The customer information, and in this case, might be duplicated across many orders, order records, and similar information may as well be duplicated. So we get an increase in data storage size and data that must be kept consistent, but at of course the benefit of faster single write or faster read mostly actually. But of course, so there is a middle ground that can be found between both approaches here. Some fast read and at the expense of slightly more data redundancy, that would be ideal, but finding this middle ground of somewhat normalized and somewhat denormalized, there are basically no guidelines, or well, there are some guidelines there, but it's really hard to really choose the right solution, the right schema. And we could, for example, demonstrate this with a user buying a product. So initially we could have the normalized case where we have products and customers separated in single tables. But we can, for example, start grouping data together, seller information along with the product record. Orders could include the buyer's information. A customer record could include all its orders, and so on and so on. So it quickly becomes quite exponential in the amount of combinatorial solutions we can check. And so modeling all of the potential solutions, this really requires a search-based tool to find the most optimal schema. So what exactly is the suitable level between normalization and denormalization? Well, a good schema involves choosing which information to group together, which entities and which relationships, and which attributes to select at each step, but also where to place indexes and partition keys. And while the solutions are vast, the ideal solution ultimately depends on your specific use case, your workload, your read operations, your write operations, and also importantly, how your data model looks like. So there's a lot of factors to take in. So it boils down to the fact that it's tremendously complex to manually choose the most ideal schema for your use case. Now, related work has done a lot towards alleviating such manual effort, and there are tools which take your data model and some portion of your workload and ultimately suggest some type of schema for columnar NoSQL databases and document database systems, but most of them apply straightforward transformations rather than enumerating all possibilities and applying cost models or heuristics to figure out the best candidates. And most of the actual generators with advanced cost models, well, they mostly exist for columnar systems. So this is where I'm alleviating the state of the art or improving the state of the art in introducing a document-based schema recommender with extensive search-based generation and pruning and ranking algorithms, which I think is quite novel when compared to the state of the art. So this is why I introduced DBSR, a document-based schema recommender for NoSQL document database systems. If we take a brief glance at the architectural overview of this recommender system, we can see that it takes as input conceptual schema, so the application's its data model, a read workload as a set of join operations, and some runtime configuration parameters which can be specified. This runtime configuration may put some bounds on the space of the solutions generated or its types, such as, for example, the level of nesting or numerous relationships embedded. We can limit that, or the number of iterations. So this is then parsed into the generator as models, and we start off by initializing the generator. This happens via the initialization of some set of initial normalized document data structures, and secondly by creating a set of root query plans over these normalized data structures. So if we take an example of a join query which merges together users with products, this would then yield the initial data document structures, one for users and one for products. So per query in the join query, we will make a structure which answers those specific queries. We will do this for each join query in step, and ultimately we might end up with a lot of variants of data structures. So then for each join query, we will then also investigate on how we can now exactly, what are all the possible ways in which we can now answer this query using the data structures that exist. So we have some initial starting points, which is somewhat worst case, and of course we can start improving from this point on by optimizing join queries and making larger documents, which is exactly what the next step will do. So the generator will select the next query plan for optimization, and it will optimize a join step by actually eliminating it through merging the merge of two documents together. So if we have the query plan which joins users with the product information that it sells, and also the specific buyer comments that were present on those products, we can optimize this query plan by merging together both users and products, or products, its comments in a single record. So this will yield users embedded with products, users that have their product information embedded, and products which have their comments or reviews embedded as well in the single record. And this will then result in the possibility of executing this query plan with 2 steps instead of 3. Subsequently, other query plans are also notified of the existence of a larger novel data structure. These query plans will then evaluate whether or not they can make use of them, and this might in turn as well yield new query plans. These plans are then also put on the stack for further optimization, which in turn creates again novel documents, etc., etc. So at a certain point, alright, this is an example of the runtime process in the generator. So at the top we see the query plan that joins users with its bids and the items which the bids were made on, and as well the person who was selling that product or that item. The generator or the query plan is then optimized by merging together bids with the users, so the person, a user record will now contain its biddings as well, and as well merging together a bidding record with the item information which the bid was placed on. So as you can see, as we move on, we get more and more query plans and more complex embedded data structures. So this is still at the briefly early stages of the generator, but it gets quickly more complex later on. So eventually, the query plans which still require optimization, this stack might grow rather large, say around 100,000 or 120,000 query plans. Eventually we will start to prune this stack by sorting the query plans from least to most effective, and then of course prune the least effective ones. We can similarly also prune documents, and then the generator can of course continue and move on and generate more. So and we will have intermittent pruning, and eventually we will apply final pruning. This final step will of course, for example, look at how many document collections are actually desired, or is there a limit? Say 10 documents, tables, or collections, which we will then prune the remaining one or the least effective one till we have achieved that subset of 10 ideal document candidates. This will then yield the schema recommendation, which features a set of document collections as well as query plans per original join query on how to answer that given query using the suggested document structures. Thirdly, we also provide insight via a matrix which shows the costs of involved queries and the cost and efficiency of certain document structures in the global space. So it really is a detailed overview and schema that the user can work with. So to zoom a bit more into the pruning aspect, which is a large factor to determine the set of solutions, we have come up with several methods to prune the ongoing solution space. And one of that is query plan auto compaction. So if there is, for example, a smaller query plan, we have, for example, query plan users with embedded products, which joins again with the products document. We could, for example, simplify that because we know there's a more simplified version of that available. So all query plans with smaller join steps are passed to query plans in a bucket with more join steps. They will see and evaluate whether or not they're redundant. So this is quite simple. But also, of course, the query plan pruning, which I talked about, which ranks all query plans based on their efficiency, and the least efficient ones are pruned. Then secondly, we also keep a ranking per document. So we define the effectiveness of a document not by the number of total query plans it appears in, but the quality and the number of query plans it appears in. So if a document appears in highly qualitative but few query plans, it's still better than, for example, appearing in many query plans which are of lower quality. And for this we define some nonlinear function. This of course could be more improved, but these are simple models and they work right now. And based on this ranking, we sort documents from least to most effective based on their global fitness. So this is more or less in the grand scheme of things how the generator or the recommender works. For more details, you can of course consult the paper or the repository on GitHub. Okay. But then we of course did an evaluation of the recommender system, and we did this in a twofold approach. So first we analyzed the generation and the pruning process of the documents, and we did this using two configuration settings. One where we limited only the height, so the number of embeddings that could be done, so 3 relationships in turn, but also increased this height and also the width at each node. For example, a single user at the top could embed both his products and his comments and some other relationship. So that's what height and width means. So one is quite narrow and the other runtime configuration also goes a bit more broad. Then we also did a performance evaluation to assess the quality of these schemas that were recommended versus a traditional or normalized approach. And when looking at this evaluation, we ran this all on the case of the online auction case, extracted or somewhat based on the Rubis benchmark, which is quite typical. It's somewhat modeled after eBay. And so we ran that recommender against that applications model, or at least part of it, and also we formulated a set of join queries over this data model. That was not extracted from the benchmark, but we somewhat based on it. And so we can see that the join query performance in most cases outperforms the normalized schema, or in the worst case, the baseline's performance is similar. And this comes from eliminating physical latency between nodes by not having to traverse data structures that across other nodes, for example, or latency between client and server when a join wasn't possible, which in the case this was, a join operation was not possible in MongoDB using horizontal distributed tables or sharded tables. But of course, this read performance gain did come at a cost of increased data redundancy, which is typical with data denormalization. But the key point takeaway is that we could achieve this schema and this performance only using 3 documents collections rather than 5 document collections, which was present in the normalized schema. So to conclude, we have presented a workload-driven state-of-the-art schema recommender for NoSQL document database systems. It's a workload-driven recommender that takes into account your data model and your join queries to group data together. And it does so in a search-based fashion, and it makes use of cost model and ranking functions for both query plans and document candidates, both which can further improve upon in future work. We eventually output a document schema and a set of query plan suggestions along with a matrix which provides insights on the efficacy of documents, as well as the cost of the query plans to execute. So some detailed insights there. Future work is definitely possible based on the analysis of our pruning process. We determined that it was maybe not so ideal to do a global optima strategy to prune documents, but perhaps some documents could be really highly efficient for a certain set of queries or from the workload, but not all of them. So it would be interesting to further investigate more local optima search-based exploration on pruning, and also in the future to include support for write queries and also balancing out the cost model or calibrating it. So I think this is a very interesting topic, and I hope you enjoyed the presentation and the work. If there are any more questions, you can of course contact me via email.